How does liquid water move? Water and life are inseparable. Being just a simple triatomic molecule, water has many anomalous properties. These peculiarities are based on the ability of water to form a dense special network of hydrogen bonds. Hydrogen bonds are strong dipole-dipole forces. How does liquid water move? The vibrating molecules of water can be represented using a toy model of masses with springs. In this way, the system is described as a harmonic oscillator, whose solutions are discrete values of energies. It is possible to bring the system out of equilibrium by shining light on it. If the light that perturbs the system has photons with exactly the same value of energy as the energy difference between one level and another, light will be absorbed and a transition will occur. This is specified explicitly in the Fermi's golden rule. It is worth noting that transitions have selection rules. The vibrational motion cannot be symmetric, it must lead to a change in the dipole moment. The radiation of light must be polarized parallel to the direction of change of the dipole moment as well. To analyze absorption, it is considered 1. The deflection of the ground state, 2. Further excitations to a higher energy level, 3. The stimulated emission from the excited state, 4. Relaxation to an intermediate state, and 5. The modified ground state. The question now is how to observe and measure these water movements. A sample is illuminated by a pump pulse, with the purpose of exciting a significant fraction of the molecules. Before they decay, a probe pulse is used to trace the spectral changes induced by the first pulse. In this manner, the frequency of the absorption can be identified, and with it, which type of vibration is in fact occurring, for example, a bending vibration, a stretching vibration, or which type of conformation have the water molecules, like strongly or weakly hydrogen bonded. The pump probe spectroscopy technique uses a specific light, which is in the mid-infrared range. The pulses of light emitted are ultra-fast, in the order of 100 femtoseconds. This technique can distinguish the difference between a homogeneous and an inhomogeneous broadening of the absorption. It can measure how the system decays over time or the lifetime of the vibrations by controlling the optical delay line between the pump and the probe pulses. In conclusion, ultra-fast mid-infrared pump probe spectroscopy allows us to study the dynamic properties of water molecules and how the motion of these molecules is affected by hydrogen bonds or by the nearby presence of other molecules.